Welcome everyone to this video. We're going to start talking about the independent particle approximation. So to lay kind of some of the groundwork for it, right, this independent particle approximation is going to be discussing essentially a type of approximation that's made for modeling molecules, okay, and the electronic states of those molecules, right? So there's different types of ways you can do modeling of molecules. There's things like semi-empirical methods, like that Huckel MO theory that we talked about. Okay, how these work. These are methods that make some gross approximations, then often fit certain parameters within the method to experiment. Okay, so these methods use fittings on certain constants in order to try to fit closer to experiment. There are what are considered wave function-based methods, so kind of molecular orbital theory methods, things like Hartree-Fock theory, perturbation theory, and this independent particle approximation will be sort of a wave function-based method. And then there's a very commonly used thing called density functional theory, okay, where instead of using kind of the wave function to solve for everything, right, you use the density, okay, which is just, you know, psi star psi. Integrated over like all coordinates but one. Okay. Basically, the reason kind of we potentially do this is the electron density is the probability distribution of finding an electron in space. Okay, and that just depends on the coordinates of one electron. The wave function depends on the coordinates of all electrons, so it's more complicated and things like that. So that's why kind of this density functional theory is very advantageous and is used quite often. All right. Now, Hartree-Fock theory as well as density functional theory are considered what are considered mean field theories. Okay, and why they're considered mean field theories is because basically you assume an electron feels an interaction with just the average kind of distribution of where all the other electrons are, right? So you can imagine, right, if you have some molecule, you have a distribution of electrons around that molecule. When we use Hartree-Fock theory or DFT to approximate interactions between electrons and things like that, we assume an electron just interacts with the kind of average distribution of where all the other electrons are, instead of like an instantaneous electron-electron interaction based off of how far each electron is as they're bouncing and moving around in space, right? And instead, you just have one electron that's kind of moving around and it's feeling the interaction with all the other ones, right? Now, each electron is considered to be moving around and everything. It's just when you think of the electron-electron interactions, we now think of an electron interacting with an average location for all the other electrons, so to speak, not an instantaneous location, okay? And that's why it's called like a mean field theory, because an electron is interacting with the average mean electric field from the other electrons, right? So the mean field, the average electric field, okay? So this Hartree-Fock theory, so I'm calling it Hartree-Fock theory. We can call it the independent particle approximation. The same thing. How this works, okay, is you use molecular orbital theory. So this starts with assuming molecular orbital theory. So your molecular orbitals are written as a combination of your atomic orbitals. Okay, so it makes that assumption using molecular orbital theory, and then from there, using the Schrödinger equation, variational principle, and things like that, you can arrive at this final equation for the energies for your electrons and your orbitals and so on and so forth, okay? And so you arrive at this final equation for the energy. We're not going to go into detail how you get there, but just trust me. This is what the energy looks like in this independent particle approximation, okay? So here, epsilon I, right, are the energies of your orbitals, okay? They include things like the kinetic energy of the electrons, the electron nuclear attraction rate. These are basically your hydrogen atom energies, okay? So they're going to be something like epsilon I is going to be a bunch of constants times the effective nuclear charge squared over n squared, okay? Right? And again, there's a bunch of constants out there. I can never remember what they are. Just things like the mass of the electron, the charge of an electron, permittivity of free space, pi, h bar, and so on and so forth. Okay, and so right, that's what these epsilon sub i's are the atomic orbital energies. Okay, and then j I sub j. Like Jij here with the subscripts I and j, this is the Coulomb repulsion between two electrons in orbitals I and orbitals j. So this Jij is like, well, I have the intervals on the next slide, so I'm not going to bother trying to write them out. But it's this Coulomb repulsion, right? Two electrons, right, feel a Coulombic repulsion between them because they're both the same charge, so opposite, same charges repel each other, right? And so there's this Coulomb repulsion, okay? And then Kij here is what's called the exchange energy, okay? And this energy, the exchange energy, is purely a quantum mechanical energy. There's no classical analog to what the exchange energy is. It has to do with the fact that your electrons are fermions. That's why it exists and things like that. And we'll go a little bit more into it in just a slide or two, okay? But I'm just noting here that the exchange energy doesn't have a classical analog, right? Like the orbital energies are related with the kinetic energy of your electrons and their attraction to the nucleus. Coulomb energy is related with electron-electron repulsion. And the exchange energy is purely a quantum mechanical effect. Okay, right? And again, it comes from the fact that you're dealing with half integer spins. So these electrons are antisymmetric. And because of that anti-symmetry, you get this kind of exchange energy term popping in, okay, which is this integral right here, okay? Psi I and psi j are different orbitals, and 1 and 2 are indicating, so 1 is indicating electron 1, right, and 2 is indicating electron 2. So these are electron labels, the 1 and 2, and then psi I and psi j, those are different orbitals, right? Okay, right, and then R1, 2 is the distance between those two electrons, right? And so that's what the exchange term is. And why it's called the exchange term is you notice that electron 1 is in orbital I and in orbital j, and electron 2 is also in orbital I, orbital j within this integral, okay? The Coulomb term, so this exact same looking thing, would be psi I1, psi I1, psi j2, psi j2 all over R1 minus R2, okay? And so, right, the difference in these integrals is here, electron 1 is just in orbital I, electron 2 is just in orbital j, and that has to do with essentially, right, psi I, like psi I times psi I is the probability of distribution of wave function I, right, like of that orbital. So what this is really, the Coulomb integral is literally take the electron density of that atomic orbital and take the electron density of a different orbital, okay, and right, and then you have these two electron densities, these distributions of electrons in space, and then literally just summing up all the different Coulomb interactions of every potential different point the electrons could be within those electron densities, and that's what the integral is related, okay? So this is literally just Coulomb repulsion between two electron distributions, okay? Again, this is a purely classical like term, okay? But again, the exchange is not. It's this exchange of the orbitals. That's why it's called exchange interactions, because it's an exchange of orbitals, okay? where electron 1 is in orbital I and orbital J. That's purely a quantum mechanical effect and quantum mechanical term. Okay. Right. And again, here's right what that Jij is. Okay. And so let's look at an example of this real quick to kind of finish up. Okay. So this is my energy term. Okay. I'm going to calculate these sums are sums over all electrons. Okay. So there's another way I can write this formula. Okay. I can also write this formula that E equals sum over I, epsilon sub I, plus the sum over I less than J of Jij minus Kij. Okay. So here, notice that there's not this factor of 1/2 here. Okay. And the reason why there's not this factor of 1/2 is because so Jij is equal to Ji. Okay. So there's this factor of 1/2 here because I'm summing up over like 1, 2, and 2, 1. Okay. And those things are the exact same, so I got to divide by 2 to make it work out. Okay. But in this bottom term here, I'm just summing up over 1, 1, or 2, 2, or I'm like summing up over 1, 2, 1, 3, 1, 4, 1, 5, and I'm not including the terms 4, 1, 4, 2, 4, 5. So it doesn't really matter. We'll see a practice of this in just a second. Okay. Right. So this is our energy term, right? And so the total energy for lithium atom, according to its independent particle approximation, is given here. Okay. So we're going to work out where we get that. Okay. Create a blank slide here to make it easier for ourselves. So I'm going to put lithium is like this. There's a 1s, 2s electrons. Okay. All right. My energy is the sum of I of epsilon I plus some. I'm going to do this I less than J type sum of Jij minus Kij. Okay. Right. And so the first thing I can do is write out all of this sum. Okay. And all I do there is write orbital, like if I'm going to label these electrons, let me use a different color here. Let's pick a blue here. This is electron 1. This is electron. I'm going to do a different color per electron. 3, and let's see yellow. Oh, this is electron 3. Go back to green here. That's not electron 3. That's electron 2. Okay, right. And so, right. And so let's see here. So electron 1, okay, is in the 1s orbital. Oops, that should be 1, not an I. So it's in the 1s orbital. So it's just epsilon 1s. Okay. And then I'm going to add to that, right, the energy for the electron 2, which is in the 2. It's also in the 1s orbital. Jeez. All right. Here, the 1s orbital. Now I'm going to add to that, right, the energy of electron 3, which is in the 2s orbital. Okay, so that's all that first sum is. Okay, that's that first sum here, right? Oh, try to change the color of my pen. Right, that's that first sum here. Okay, so now we need to do the second sum. Okay. So now we need to do this term here, right? So I'm going to do that down here. Okay, so I'm going to add this second term. Okay, what I bracketed here in purple, right? And so how I do this is now I'm adding up pairs of electrons. Okay, right? An electron isn't going to pair with itself, right? So I'm not including like electron 1 interacting with electron 1. Okay, only including things like electron 1 interacting with electron 2 and 1 interacting with 3. Okay, and because I've done this sum as like I greater than J, what I'm going to do is if I'm looking at electron 1, I'm only considering electrons with numbers greater than 1, right? If I'm looking at electron 2, I only consider electrons that are, higher than 2, right? And how I've labeled these electrons, I typically do this, where I start labeling my electrons from the bottom left and go right, and then up and right, right? So I'm going left to right and then up, okay? And label my electrons. So now, when I'm filling out these Coulomb terms, right, I have this J 1s 2s term for electron 1 with electron 2, and then I add to it my J 1s 3s term for electron 1 with electron 3, okay? And then I need to do the, I'm going to do the Coulomb term, or that was the Coulomb, I'm going to do the exchange term, right? Oh shoot. The one thing I forgot to mention about the exchange, it's very key, okay, right? Right, and it's written on the slides, but I forgot to highlight that. Right, Kij only exists for same spin electrons, okay? So for example, in this example here, electron 1 is spin up and electron 3 is spin up. So so the exchange term here, okay, so this minus K1s only exists with electron 3s, okay? There is no K1s2s because K1s2s has electrons of opposite spin, so those do not exist, okay? Right? All right, and so now I'm done with electron 1. So now I'm going to add the terms dealing with electron 2. So I have J2s, and it's only going to interact with 3s, because again, because I'm not dividing by 2, right, I want to consider all of the unique interactions. The only unique interaction with electron 2 that I haven't already considered is 2s with 3s, okay? Those have opposite spins with each other, so those are not going to have an exchange term, okay? And then that's it. Those are all my terms here. So now my total energy here, my final total energy, if I simplify this, is 2 epsilon 1s plus epsilon 2s plus J1s 1s. All right, so I mislabeled these things. All right, so let's fix these labels, sorry. I'm confusing myself with electron numbers versus orbital numbers, right? This is electron 1's in the 1s orbital, electron 2 is in the 1s orbital, okay? And electron 3 is in the 2s orbital, okay? So, right, so that's obviously a common mistake. I just did it myself, right, where I'm messing myself up with my electron numbers versus my orbital numbers, right? You don't have to write down these numbers for your electrons if you want to kind of keep track of it in your head, and maybe you won't get as confused as I did, right? But then here, 2J1S2S, okay, then minus K1S2S, okay? And so this is the final energy for lithium atom, okay? Right, and so that final energy, right, just a couple of notes about them, right? Epsilon i's are always negative numbers, right? The atom orbital energies for a hydrogen atom are always negative, okay? So, right, the lower the quantum number, 1, 2, 3, 4, 5, right, the lower the energy, okay? And the Coulomb and exchange terms are always positive because they come from electron-electron type repulsion. So these are always positive interactions, okay? So, right, and so these lower your energy, okay? The orbital energies lower your energy, but then the Coulomb repulsion raises your energy, okay? And then this exchange term actually helps lower the energy, okay? And so this exchange interaction is actually a favorable interaction that lowers the energy, as we see in the next video with another example of this, right? This exchange term is very helpful in stabilizing certain atoms and molecules in certain ways, okay? It's very key. So this exchange, purely quantum mechanical energy, is very key to explaining how lots of trends and things that we know happen in atoms and molecules, okay? So that will be it for this independent particle approximation video. Hopefully helped kind of introduce the idea of what this independent particle approximation is and how we, given electron configuration, how we can calculate what the energy is given in the independent particle approximation.